This is the last video and big concept of our unit on momentum, and it takes everything that we talked about yesterday with the law of conservation of momentum and applies it to some problems about collisions. At the end of this video, you're going to be able to use the law of conservation of momentum to determine the final velocity of a system, of objects in a system, after a collision. We're going to work through two practice problems on here. You should write everything down to have some good examples, and then you can use that to help you through the practice problem set. Here's our first problem. Tim is roller skating with his son Scott. Tim has a mass of 80 kilograms and Scott has a mass of 40 kilograms. They both start at rest, then Tim pushes Scott. If Tim moved backwards at a velocity of 20 meters per second, what's Scott's velocity? Now I know what you're probably thinking. But don't get frustrated. Just take a deep breath. And I know what that WTF stands for. What's the force? But that's not even the appropriate question. Take a deep breath, and the first question I want you to ask on a problem like this is this collision elastic or inelastic? And you have to remember the definition of both. Remember, elastic collisions are bouncy collisions, and inelastic collisions are sticky collisions. So let's look at this one. Is this collision elastic or inelastic? Are Tim and Scott stuck together, or are they moving apart? Before the collision, they're together, but after the collision, they're moving apart. So, this would be an example of an elastic collision, where they're moving apart. As soon as you identify that this is an elastic collision, we're going to proceed in a specific way. Let me explain. Now remember yesterday we talked about the law of conservation of momentum, where we said that the momentum of objects might change, like Scott or Tim, but the momentum of a whole system is going to remain the same unless acted by on an external force. So, when we look at this whole system of Tim and Scott, the force took place right here. So there's no external force. And that means that the initial momentum of the system is going to be the same as the final momentum of the system. Now let's plug some things in that we know already. Make it a little bit more mathy. Instead of using those words, let's use some symbols. Remember, P is momentum. So the momentum of object 1 initially plus the momentum of object 2 initially equals the final momentum of object 1 and the final momentum of object 2 added together. Does that make sense? The momentum of each object before and after when you add them together is equal. The law of conservation of momentum written in a different way. Let's write it in yet another way by substituting each of these P's with another one of our formulas. If we know that P equals mv, let's swap each of those P's out for mv and see what that looks like. So here's the same formula, but instead of writing P, we've written mv. So the mass of object 1 and its initial velocity is its initial momentum. If you add that to the mass of object 2 times its initial velocity, that's its momentum. And that's going to equal the final velocity. The mass of object 1 times its final velocity plus the mass of object 2 plus its final velocity. Let's put it to work with this problem. I'm going to give us some more space. There we go. So, let's start underlining some stuff in this problem that we can use. It says that Tim has a mass of 80 kilograms. And Scott has a mass of 40 kilograms. They both start at rest, And when Tim pushes Scott, Tim moves backwards at a velocity of 20 meters per second. And it says, what's Scott's velocity? Well, if this is backwards at 20 meters per second, we're going to have to set some positives and negatives here. So, let's set Tim's velocity backwards at 20 meters per second. And we know that Scott is going to move the other way. And we're all set. And this looks pretty complicated, but it's actually not too bad. So, Scott's mass is 40 kilograms, but his initial velocity is 0. So his initial momentum is 0. Tim's initial velocity is 0, so that makes his initial momentum 0. Then, what we have over here is 40 times the velocity of object 1, final, plus 80 times negative 20. Let's go through and solve that with our calculators, plug in some numbers. Now I'm just going to put an x here instead of velocity 1 final. And if you take your calculator and multiply 80 by 20, you'll get 1600. So what we have here is 0 equals 40x plus 1600. We can add 1600 to both sides and get 1600 equals 40x. Then divide both sides by 40, and you get Scott's final velocity as 1600 divided by 40, and that's 40 meters per second. I know that was kind of tough and it's going to take a little bit of practice, but stop the video, go back and write this down. It'll help you out later on. Now let's move on to our second problem. This one says Debbie is at rest on ice skates when someone throws a 15 kilogram ball at her with a velocity of 6 meters per second. Debbie catches the ball, and both Debbie and the ball move backwards. If Debbie has a mass of 60 kilograms, what is the velocity of Debbie holding the ball? And this would be after the collision of Debbie with the ball. So, remember, what's the first question you ask? Not WTF, but ask if this is an elastic or inelastic collision. After the collision, Debbie and the ball are stuck together. So, this would be inelastic. So an inelastic collision, we approach a different way. That's why the first question you ask has to be, is this elastic or inelastic? It's still the same thing with the initial momentum of the system being equal to the final momentum of the system. But the fact that these two are stuck together lets us change our approach and use a different formula. Again, here's the initial momentum of object 1, the ball, and the initial momentum of object 2, Debbie. But what happens in the final momentum is, since they're stuck together, we treat them like one object. How does that change this formula? Let's look. So we have the mass and the initial velocity of the ball plus the mass and the initial velocity of Deb, and that's going to equal the final velocity of the ball plus Deb's mass. Now the reason we only have one velocity here is because these two are moving together because they're stuck, because this was an inelastic collision. So let's work through this and give ourselves a little more space. Let's identify some key things from the problem. So we see that the ball is 15 kilograms, and we see that it was thrown at her with a velocity of 6 meters per second. Debbie's at rest to start with, and she has a mass of 60 kilograms. That's enough to get going on this. Alright, so we have the ball has a mass of 15 kilograms. and its initial velocity is 6 meters per second. Since Deb is at rest, her initial momentum is 0. We want to find out the final velocity, and we have to multiply the final velocity by the sum of the two masses. The ball has a mass of 15 kilograms, and Debbie has a mass of 60 kilograms. Now we're ready to rock and roll, and it seems like a lot of numbers, but as long as you work through it and start simplifying, I think you're going to find that it's okay. So use your calculator to do 6 times 15. You're going to find that that's 90. And 90 plus 0 is 0. And we have the final velocity. And in here is 75 kilograms. Now to get this final velocity by itself, we have to divide both sides by 75. So let's do that in our calculators. 90 divided by 75 equals 1.2. So the final velocity of those together is 1.2 meters per second. Now you have to ask yourself, does that make sense? When Debbie catches that ball, will they be moving slower or faster than 6 meters per second? Slower, right? Because now the system, or the thing that's moving, is more massive. So those are two example problems. Hang in there and do your problem set. If you need help, ask for help. We're going to do plenty of these problems before you're going to be tested or quizzed. So don't get too frustrated. Embrace the awkwardness, ask for help, and you're going to get through this.